Hello, everybody, and thank you for the invitation. My name is Daniela Petti, and I'm from Politecnico di Milano. Today, I will speak about nanoscale engineered spin texture for magnonics. First of all, I would like to thank all the collaborators to this project, among all people from Politecnico di Milano, especially Eduardo Albisetti, people from University of Perugia, from PSI, and Elisa Riedo from NYU. This is the outlook for my presentation. First, I will give you the motivation of this work, that is the control at the nanoscale of the magnetic properties of materials. Then I will introduce thermally assisted magnetic scanning probe lithography, and I will show you how to use this technique for patterning spin texture at the nanoscale. And then I will show you an application that is the control of spin waves with this spin texture. So far, the patterning of magnetic material has relied on two main techniques. One is optical or e-beam lithography, and the other is ion irradiation. In optical or e-beam lithography, the material is shaped at the nano or micrometer scale by adding or removing materials. In this way, by exploiting shape anisotropy, it is possible to control the magnetization direction or the anisotropy, as in this nice zigzag figure on the left top, or in this dot in the bottom left of the slide. Ion radiation relies on the use of suitable mask to locally implant ions. In this way, it is possible to locally control the magnetic properties of materials by chemical modification or by displacing of atoms. What these two techniques have in common is that both are mostly destructive and irreversible. So once you put a functionality on in your materials, this functionality is fixed once at all. So can we imagine a technique in which we can control the magnetic properties, but to add a reconfigurability of the system and the technique? And the answer is yes, we can think about it. And this technique is based on thermally assisted scanning probe lithography. ta-SPL is based on the use of a heatable scanning probe to realize a physico-chemical modification of the surface of materials at the nanoscale. It was invented in the 90s by IBM for storage purpose, when they realized that heat can be confined at the nanoscale using a tip of an atomic force microscope. This tip is made of two arms of highly doped silicon in which a current is flowing, and the resistive heater made of intrinsic silicon at the back of the tip apex. In this way, by choosing the current applied, so the voltage applied to the system, it is possible to tune the temperature of the tip. And the final tunability is demonstrated here on the bottom, in which we have the applied voltage, and in red the heater temperature that can reach up to 1000 Celsius degree. Starting from the first proof of principle, with a different application has been demonstrated. First of all, the nanoscale reduction of graphene here in the center, in which the conductive paths are patterned in this graphene oxide. Or the creation of a 3D topography by using the sublimation of a polymer and creating, for instance, this nice Matterhorn 3D figure. By tuning the temperature of the tip, is even possible to create chemical or protein gradients on a substrate. And finally, this on the bottom right, this last recent result is the use of ta-SPL in combination with the resist in order to create ohmic contacts of very sensitive materials like 2D materials without damaging them. So how can we apply this technique for magnetism? The answer is providing the right substrate. So in a simple ferromagnet, what we have is that at remanence we can have two different directions of the orientation depending on the hysteresis loop. But now if we move to a different system, an exchange bias one, the exchange interaction at the interface between the ferromagnet and the antiferromagnet spins the spins of the ferromagnet in one direction, so that the hysteresis loop is shifted here on the left, for instance, on a quantity called exchange bias at a remanence. We have that only one possible state of the magnetization is present. We can set this exchange bias by performing a heating and cooling of the sample. So from the left, we start with the system initialized in one direction. In this case, the spin of the ferromagnets are pins towards the left. Then we move and we heat up the system up to a temperature that is called blocking temperature, that is just below the net temperature of the antiferromagnet. In this case, the antiferromagnet is disordered and the spins at the interface are unlocked. So we can apply now an external field that is able to orient, for instance, the spin in another direction. Here we have towards the right direction, and then we cool down the sample, making a process so-called field cooling. And now, if now we remove the field, we have a situation here in which the exchange bias field is set in another direction. At the remanence, the magnetization state is different from the previous one. This is a well-known procedure that has been used in thermal system and RAM, for instance. The idea of thermally assisted magnetic scanning probe lithography is to make this process at the nanoscale. So here we start with the system initialized in one direction. So the yellow spin of the ferromagnets are all pointing towards the, for instance, here the right. Then on the center, we apply an external magnetic field of another direction. At the same time, we scan the heatable tip on the surface. So only in the region when the tip passes, the heating of the sample occurs, and when the tip moves away from that region, a field cooling is performed. In this way, a new direction of the exchange bias is set, and here you can see the green line. Now, a green spin, sorry, of the antiferromagnet. Now, if we remove the field, what happens is that if the exchange bias is strong enough, domains, regions, or domains with different magnetization at remanence are created here in the red of the sketch. And so a new exchange bias has been set, and in this case, the corresponding hysteresis loop is shifted on the right. So this technique is simple step, non-destructive. It doesn't require a clean room environment. And as you will see, it is reconfigurable because exchange bias is reconfigurable, is robust against external perturbation, and also I will show you that is finely tunable. These are the first results. Here there are domains pattern with different shape with the exchange bias set in anti-parallel to the one of the previous field. This is a magnetic force microscope image, so we are sensitive to the magnetism. And if we compare this figure with the figure of the topography, we can see here that on the topography there is nothing, since the pattern is purely magnetic. Now, if we compare this result with micromagnetic simulation, apart from the good agreement with the data, what we can appreciate here on the bottom panel is that by controlling the shape of the pattern domains respect with the external field, we can create a domain wall with of different nature. For instance, here we have a tail-to-tail domain wall that in a continuous film originally, naturally cannot be sustained. These domains that are created, of course, respond to weak fields. So we have the so-called breathing of a domain. Here the domain are reduced or expanded depending on the applied field, but what is important is that at remanence, we have always the same situation that is the one that is also measured with the MFM. As I mentioned before, this technique is tunable. So on the left, we can see that it's possible to tune the anisotropy strength. This is a polycrystalline sample. So by tuning the temperature of the tip, exchange bias with different strengths can be created, as you can see here in the micro-Kerr hysteresis loop acquired in different pattern regions. Also, the direction can be tuned, so we can imagine by changing the direction of the writing field to right domain with different direction of the magnetization at remanence. And on the right, you can see here also that it's possible to write, erase a rewrite. In this case, we write a square, then we erase only the left square, and then we write a triangle on top of it. So far, I show you the patterning of domain, but in the very same system, we can also think to move to 1D and 0D structure. Here, if we start with a uniform domain and then we pattern a region with exchange bias or magnetization in the opposite direction, we can create an L wall. But now, if we pattern the two regions at the two side of the domain walls, on the top and on the bottom here, the violet one, we can fix the chirality of this wall. And then if we imagine to write, for instance, one of the two, the one domain with the magnetization anti-parallel to the other one, we can create an L wall, a vortex line within the L wall. These are the experimental results. In the center panel, you can see the MFM image of a vortex block line or an anti-vortex block line. This can be stabilized by choosing the direction of the magnetization in the fourth region of the sample shown here on the left. And here you can see on the right, again, the simulation. We can also think to other structure, for instance, vortex anti-vortex pair. Here we have this square structure with a magnetization that is has a circularity in the counterclockwise direction. So we have a counterclockwise chirality. And here the vortex is in the middle and the anti-vortex is on the left bottom part of the figure. On the bottom panels, you can see that by reversing the direction of the magnetization, the clockwise chirality is stabilized. And in this case, the anti-vortex is on the top angle of the figure. So by choosing the geometry of the pattern and the direction of the magnetization, a lattice of vortex or an anti-vortex pair, for instance, can be stabilized. Finally, here are some simulations that show that the block lines that are shown before can be also displayed in the L wall that has been patterned. So in this case, we can really think to write some conduits from this, some circuit of this vortex block line made of domain wall. I show the results in exchange bias system, but we can also imagine to apply this technique to other systems. And for instance, here I report the results of synthetic antiferromagnets. This is the hysteresis loop of our system that is also exchange bias. So the idea is the two cobalt iron boron layer are coupled anti-parallel at remanence. Here is shown by this nice plateau by bilayer coupling. And the top iron cobalt boron layer is exchange bias to iridium manganese. So the idea is that if we are able to write exchange bias, so control the magnetization of the top cobalt iron boron, point by point, we have fixed also the magnetization to the bottom ferromagnetic layer due to the bilayer coupling. And these are indeed the result in which we can see the MFM image. This is a compensated system. So as I will show you afterward, the signal is arising only from the domain wall. And in violet, this is the direction of the magnetization in the top layer, while in the bottom, of course, is anti-parallel to the top one. And finally, the last system is an out-of-plane exchange bias system. Here is a nice figure of the logo of Politecnico di Milano, in which here the MFM white and dark contrast is due to the out-of-plane component of the magnetization. And since this system display DMI, the domain wall are chiral, so the idea is to stabilize skyrmion phase, skyrmion lattices, and to maybe create some conduits for this skyrmion. So this is a working still in progress. In summary, I show you that different spin texture and different in-plane, out-of-plane, or subsystem can be patterned with this technique. And now we move to the application. And the application is related to spin waves, because spin waves, as you can see here from this simulation, has an isotropic excitation and propagation, which depends on at the end on the direction of the magnetization. So the idea is to exploit the control of the direction of the magnetization to control spin waves. Of course, there are a lot of work on it, and I will show you our example. Here, I will show you how we control spin wave emission with pattern domains. Then I will show you how to create spin wave circuits with domain walls. And in the end, I will show you how to create a nano-optic-inspired platform based on synthetic antiferromagnets. Of course, there is a lot of work in progress. Here I put some other reference on nice work on manipulation of spin wave with the spin texture. Of course, it's not exhaustive. So the first work we made, the first demonstration was this. In this sample, that is a simple exchange bias sample, we pattern these tracks with the magnetization at 90 degrees. So this on the top is the optical image of the sample, in which we see only the coplanar waveguide, because as I said before, the patterning with tam-SPL is only magnetic. So in one case, the magnetization in the domain is parallel, and the other case is perpendicular to the coplanar. Then we perform Brillouin light scattering measurement at the microscale, and we make a scan in the x direction, so parallel to the coplanar. And we can see here in the bottom the results. Only in the domain, so in the tracks in which the magnetization is parallel to the coplanar, a signal is present. That means that an excitation is present only in the tracks with the right geometry of the magnetization. But then if we make a scan also in the y direction, so perpendicular to the strip line, and we move from it, we can see that only in these A tracks with the magnetization along the x direction, a propagating spin wave is measured. That is propagating up to several microns, while in the other domains, the spin waves does not propagate. So it is possible to localize and control the propagation and the excitation of spin waves. As I said before, this is the MFM image of the pattern. Here we have only two stripes, but the idea is that this pattern respond, of course, to external magnetic field, while at remanence we recover always the same situation. So in this case, we demonstrate that we can switch on and switch off the excitation. Here we have in the center panel the brilliant light scattering measurement at remanence, in which we can see here again that the excitation is localized only in some of the tracks. Now, if we apply the external magnetic field, we have a configuration here. The field is in the y direction, in which all the domains are in the wrong, let's say, situation. So the magnetization is perpendicular to the coplanar, and so we have no excitation. These are the corresponding spectra in which we see that there is no, as I mentioned before, excitation here in red and no excitation at all. So we can in real time also control and tune, switch on and switch off this confine and control excitation of spin wave. Then we move to the nanoscale. So we pattern spin detection, basically domain walls, in order to create a nanomagnonics device. To do this, we move to space and time resolve experiment at PSI via STXM, in which we can achieve a space resolution of 20 nanometers and the time resolution up to 7 gigahertz. So in this case, as I mentioned before, we use always the exchange bias system with straight, and we pattern first straight and curved Nel wall. Here, the STXM image show a black and white contrast related to the in-plane component of the magnetization, and it arises from the different absorption of X-ray due to circular dichroism. In black, you can see here the strip line that is exciting the spin wave in the wall. And in the bottom, you can see the simulation of this pattern geometry. Here you can see the time resolve experiment, in which the black and white contrast in the movie is related to the variation of the in-plane component of the magnetization. And here you can appreciate how spin wave is propagating inside a straight and curved wall and is confined to it. The mode of these spin waves is very complicated, but also well known, and is called winter mode. And it is composed by a domain wall oscillation plus a precession of the spin inside the wall. We check the dispersion, and our experimental data are in good agreement with the simulation. And also we check that these spin waves are really propagating perturbation, and this is the phase of the excitation as a function of the distance from the strip line, and the space is changing. So this means that this is propagating spin waves. Then we demonstrate the possibility of patterning a circuit based on two Nel walls that are sharing a common apex. And the time resolve experiment is reported here. We complicated a little the thing because all the other experiments were performed at remanence. Here we apply an external magnetic field in order to tune the distance between the two domain walls. And if we here have this situation with 2 millitesla applied, we see that the two domain walls are well separated, as well as the two spin waves here in the movie that are propagating confined in the wall and then not interacting at all. See here, this is also can be confirmed by the amplitude of the excitation that is taken here along this green line and is reported on the right panel. Then we decrease the field applied, and we reach a situation in which the two domain walls here at the bottom are sharing the same apex, so they are intersecting. And here you can see that the spin waves that are following the domain wall are in correspondence with this green line are superimposed. And indeed, here in the amplitude, the two peaks are well superimposed one on each other. So this is the first demonstration that this spin texture-based circuit can be used to superimpose spin waves and eventually to make them interfere. Finally, this is the last system I show you today. That is, as I mentioned, an optically-inspired platform based on synthetic antiferromagnets in this case. The idea starts from this nice work in which, that is shown here on the left, in which they use these plasmonic nanoantennas in order to convert the global electric field in a local simulation of plasmons that are launched in this graphene layer. And the idea is to combine this mechanism with the use of spin texture that has been demonstrated to act as a spin wave emitters by this nice work of Sebastian Wins. So what we have done is to pattern engineer nanoantennas based on spin texture in order to convert the global Earth field to the nanoscale and create a shaped wavefront in synthetic antiferromagnets. The idea of the spin wave mechanism is the following. Here on the top left, you can see a simulation of a domain wall that has been patterned in this subsystem. And in particular, here in the simulation, the color code is related to the Z component of the magnetization within the domain wall. And you can see that a not negligible component out of plane of the magnetization is present at the two sides of the domain wall that has been patterned. So now if we place a straight line next to our domain wall, we are able to excite it by using the global Earth field of the strip line. And in particular, here on the right, you will see that the out-of-plane component of the Earth field generated with the strip line is coupled with the out-of-plane component of the magnetization inside the wall and is able to excite the wall, which in turn give rise to a propagating spin waves that are propagated from the domain wall. This is worth to notice that this CIS mechanism is very robust with respect to the orientation of the strip line depends on with respect to the direction of the spin wave of the spin texture, and this has been exploited in our experiment here. This is again a STXM image in which, in this case, the black and white contrast is due to the variation of the out-of-plane component of the magnetization. And here you can see on the right that a straight wall is able to excite planar wavefront, while a vortex excite radial wavefront, while a curved domain wall is able to excite shaped wavefront. In this synthetic antiferromagnetic system, this wavelength of the spin waves is very short, even at low frequency, is 300 nanometers here at 1.5 gigahertz. And you can appreciate here by measuring the amplitude of the variation of the Z component of the magnetization along this yellow line, that the spin waves are propagating along several a distance corresponding to several wavelengths. Now, by patterning, for instance, a convex domain wall here on the left, you can see that it's possible to focus the spin waves up to the diffraction limit. Indeed, here the amplitude of the oscillation along this red line is about 340 nanometers. And by patterning multiple sources, here we have a vortex at the domain wall, it's possible to create nice interference figures that are robust against defects, for instance. And this is due to the fact that the subsystem is strongly non-reciprocal, above all at this frequency. So now I'm going to the conclusion. I show you what kind of spin texture we can pattern with our system in a different exchange bias system, and I show you some example on how we can use spin texture that are patterned via tam-SPL to manipulate, emit spin waves with different properties. So I thank you all for the attention. I thanks again the collaborators, fundings, and finally a short advertise. We are hiring, so we are looking for motivated PhD and postdoc for this European project. And if you are interested, please contact me. Thank you again.